Thank you very much. It's a great honor and pleasure to be here. I must apologize in the very beginning because I'm not talking about any compounds that will contain oxygen. So I still hope that I will not bore you too much. I'm going to talk about structural complexity in binary intermetallic compounds. Sorry for that. So there are actually two topics I would like to talk about. The first one is a metastable phase in the gold silicon system. And the second topic is binary phases in rare earth engineering system. And what both topics have in common is that the phases were known or anticipated for quite a long time. In the case of the gold silicon phase, actually since the 1930s. And I have been attempting to solve those fairly long-standing problems. And they also have the synthesis method in common. They were synthesized by high temperature methods, specifically by ion melting, where you place your raw materials in a copper heart and then you melt the precursors with an ion, or by step cooling, and either of these methods is then followed by quenching. And then I would like to start with the first topic. This is the gold silicon system, and there the idea was that you have predefined classes in the melt, but still there was no binary compound known. And the system is in general important for different reasons. One being you can grow silicon nanowires from these systems. Then this was also the first system, I believe, where the metallic glass formation was discovered, and also for other reasons a lot of attention has been paid to the system. And not only me, but what attracted my interest was this deep eutectic in the system comparing to the fairly high melting points that is deeply incising eutectic. And the idea was that there must be a certain driving force to enhance the stability of this liquid. And the concept was that potentially there are some classes that are already predefined in the melt. And I was attempting to freeze these classes out into a solid by quenching. So what I did, I was using these high temperature methods, quenched at this composition, and obtained the phase gold for silicon. This is how reconstructed single crystal diffraction patterns look like. So the first, if you run an automatic search for a cell, what you get is an inner-centered cubic cell with these lattice parameters of about 5.5 angstrom, but a closer look shows that this is actually not the right solution, because here around these around this extinct reflection, there are in fact superstructure reflections, and also the intensity here is unbalanced, pointing towards deviation from a cubic symmetry. And these simple pattern would resemble the platinum mercury 4 type, but what we get in fact is new structure type that is the superstructure of this type, and one of the axes is 3-fold. And 3 times, I'm sorry, it is 3 times as well. And the structure contains these visited phenoids of gold around silicon, and these are tilted alternatingly and resemble somewhat tilting modes that can be, for example, found in perovskites. And then in these voids formed by gold is structural mode is a stellar quadrangular that is, for example, found in the methyl lithium compound, but also various other compounds. And coming back to the proposition from the beginning that there are potentially already predefined clusters found in the melt, if we are taking the 4 shortest distances in the visited phenoid into account, they are between 2.5 to 2.6 angstrom, and these are reasonably close to gold silicon interactions of nearest neighbors that were measured in eutectic melts. So, of course, it needs to be investigated further in the future, but potentially there are already predefined clusters found. And one thing that I noticed working with this compound, when, like, fresh after the synthesis, samples are bright silver, but within a few hours they actually turn golden gold. And measuring the powder diffraction over time, it has turned out that the amount of the compound decreases over time and more gold is observed. And applying the formula for the K, it is possible to calculate a half-life time of about 7 days. And this leads me to the second topic. These are the chimney ladder structures in these systems with rare earth metals and ruthenium. And the interest is verified by the potential to have strongly modulated systems with magnetic component. One of the landmark papers for rare earth ruthenium systems was made by a group of Palazzona and Panama. And what they found was firstly these rare earth 44 ruthenium 25 compounds, and for all the different rare earth metals, only one was actually, the structure was determined by a single crystal diffraction, all others were done by powder diffraction. And in addition, also bases with an actually not known composition were recorded. The suggestion was that one of the axes is very long, and then the unit cell would contain quite a high number of atoms. And this was actually a project that Sven Levin was interested in, and I was working with him on this topic. And just to introduce the yttrium 44 ruthenium 25 compound to have an idea of the structure. So this structure contains the 1 square antiprisms, and on the other hand, these tetrahedra, and they match up in case of the square antiprisms of the 1, 2, 3, 4, 5, 6, 7, 8, 9. And in case of tetrahedra, after the 1, 2, 4, 5, 6, 7, 8 period. And then comparing this yttrium compound that I have just shown you to these other praseodymium, lanthanum, and neodymium compounds where the structure was still not assigned, you can see that there are certain similarities, but looking at these satellite reflections, there are certain differences. And as I was working on specifically the neodymium-ruthenium system, I would like to comment a little bit further on the neodymium samples. So as said before, the samples were again synthesized by high temperature methods followed by quenching. And coming back to the structural units that I already introduced for the yttrium-ruthenium compound. So the period for the square antiprisms and the tetrahedra is similar to what is found in the yttrium-ruthenium compound, but for what is here marked in yellow, this row of reflections matches up again of the, so here not, here not, here not, but here in the fourth row. And then in case of the tetrahedra, then again of the second row. And taking then the sum of the extinctions that are found into account, you can assign the superspace new pair of G4 over NNC, and it is also possible to assign atomic positions, but still the problem is remaining that the R values, especially for the higher order satellites, are too poor to actually publish a structure like that. So they are beyond 20%. And this is not possible to publish at the moment. And the reason is, though, taking a closer look here at the satellites, if you look here at the even rows, this would be the main reflection, and overlapping here, you actually get a satellite of the 22nd order. And this is basically the same story and for all the higher order satellites. And if you're going to the uneven row, things are even getting worse. So there is fairly strong overlap between those reflections. And the problem, the problem that is arising from that is if, so this is just a plot over the intensities. Here are these strong satellites of the relatively low orders, and then in between there are these higher order satellites, and this corrupts the intensities that are observed. And this is the case where the satellites are fairly good resolved, but if you're looking then at rows like this, there is not only one set of higher order satellites in between, but there are actually several sets of higher order satellites. And then the intensities are overlapping, and this is what is causing those relatively poor R values for the higher order satellites. And it is not in that sense problem that the measurement conditions were not good enough. So it was measured at the synchrotron, so it was not that we were just doing that at home source. So this is actually a problem where a different data evaluation strategy must be applied. And the first thing that was done was the reflections are actually assigned by hand. So I have at home a huge stack of paper where I made cuts, and I was assigning all of these by hand, about 50,000 reflections. So it takes a while, and then we need to apply a second step of quality control, where we actually take a look which reflection can be used for the actual refinement, where we get the intrinsic intensity and not the one that is corrupted by the overlap of the neighboring reflections. And the step that we are currently spending time on is making the data evaluation better and then applying more quality control to hopefully in the end get good R values and hopefully publish the structure at some point. And of course, I'm very grateful to the direct collaborators and of course to everybody else that has been working with me in the past. And with this, I would like to thank you very much for your attention, and I hope that there are some questions despite the broader external topic.